So we start by talking about number theory and the real number system. What exactly is that? Well, we start by defining certain types of numbers. We differentiate between different kinds of numbers. So number theory is concerned with the properties of numbers, sometimes just the numbers used for counting. We will define a special set of numbers. We will call them the natural numbers. The natural numbers. And they're called that for a very exact reason. It's because that's naturally what you think of when you think of numbers. So the natural numbers will be the positive whole numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You see these little brackets around it? These are called set brackets. We'll discuss those later more specifically, but those just tell you that they are a set, meaning they're a collection of objects. There is a smallest natural number, 1. Is there a largest natural number? No. Someone tell me what's the largest number you can think of. Go ahead. The largest number. How much money would you like to have in your bank account tomorrow? $12 billion. Is there a number larger than 12 billion? That's right. You can have 12 billion and 1. You can have 13 billion. You can have 22 trillion. So there is no largest number. You can keep getting larger and larger. You can just add 1 to whatever number you want. So that's why we have to symbolize the fact that there is no largest number. We use the ellipses points there, the dot, dot, dot. Whenever you multiply natural numbers together, you call each of the individual pieces factors. 2 times 12 is 24. So 2 and 12 are factors of 24. But you'll notice 24 has other factors, 3 and 8, 6 and 4. All of those serve as factors. Now, if you're talking about 2 natural numbers, you want to talk about whether one number is divisible by another. Basically, A is divisible by B if the operation of dividing the number A by the number B has no remainder, leaves a remainder of 0. What you can say then, you can symbolize that as B, and then they use a nice vertical bar. B divides A. And it's very simple. That's because you can say 12 divides 24. 12 can cut up 24 into an even number of pieces, no remainder. Now, it's kind of weird because normally you say 24 divided by 12. Here, we're just flipping the order of it, but it's the same thing. 12 is dividing into 24. 24 is being divided by 12. Now, 13 does not divide 24. So if I try to write 13 divides 24 here, I am incorrect. It does not leave a remainder of 0. It does not cleanly divide into it at all. So we're going to have to use, whenever we use the divides symbol, we use, well, somehow it just disappeared. Oh, I see. We have to cross through the divides symbol. You cross through it with a line, basically. Say, no, 13 does not divide 24. So it's pretty simple. Does 2 divide 25? No, because 25 is not an even number. 2 cannot divide cleanly into 25. So basically, some of the things we start off in this course are pretty elementary. Stuff that you've probably seen before, or maybe it's just new vocabulary for concepts you have already seen and understood before. And of course, please feel free to ask questions at any time. Whether you're in the Zoomosphere, you can ask questions in the chat box, and it should flag me and say, hey, someone made a comment in the chat box, and I'll go check it out. Just remember, you are on a screen that the whole class can see, so just don't, I don't know, say something weird or inappropriate. So now we're going to talk about prime numbers. Prime numbers, they're not, and I can't believe I'm going to make this joke. My father would be proud. Prime numbers are not numbers you buy from Amazon. Please ignore that joke. It's a very terrible joke. And if you liked that joke, you don't have to pretend to like jokes here. I call this a joke laboratory. Yeah, we learned some math, but I also want to express some jokes. And they're not ever going to be funny. Why? Because in order to advance my career, to become better at math or statistics, whatever, I've had to let go of my comedy. I've had to let go of it. It's gone. It is no longer a part of me. So next time I make a joke, I promise you guys will not laugh. And by saying that, I've actually put some sympathy in your hearts so that next time I make a joke, you actually will laugh, but you'll laugh out of sympathy. So anyways, prime numbers. A prime number is a natural number. We know what a natural number is now. It's a whole positive number. A prime number is a natural number greater than 1 that can only be divided by itself in 1. Let's list out the prime numbers. But here's a hint. I can't list all of them out. 1 is not considered a prime number. It's tempting to consider it a prime number, but it is not. It's not prime, and there's some very good reasons for it not to be. 2, though, is a prime number. It's the only even prime number. Every other prime number must be odd, because if you had any other number that was even, it could be divided by 2. So 2 only has 1 and 2 as factors. 3 only has 1 and 3 as factors. 4, you could do 1 times 4, but you could also do 2 times 2. So 4 is not a prime number. 5 is. 6 can be expressed as 2 times 3, so 6 is not prime. 7, you can only do 7 times 1. And again, we're not doing any fractions or any weird numbers. They have to be natural numbers. 8 is certainly not prime. 9 is certainly not prime. You can do 3 times 3. 10's not prime. 11 is. Then 13, 17, 19, 23, 29, 31. As of this lecture, January 13th, 2021, we have not found the largest prime number. But that's actually not an easy problem at all. In fact, in mathematics, there's something called millennium problems. There are 6 millennium problems floating around right now. They're really difficult math problems that don't yet have a solution. And if someone does solve them, they get, I think it's $1 million prize for any one of them. So they are very difficult. One of the 6 millennium problems is, can you find a pattern to the prime numbers? And right now, no one has found a pattern even after years and years of mathematical research. So just kind of an interesting idea. So the prime numbers, they keep going, but we don't exactly have a pattern. I think last year, the next largest prime number was found using computers. It was like one of those hilariously massive numbers. If I wrote the number out, it would take like all 3 whiteboards in this room, plus maybe all the whiteboards on every every room on this campus. So that's kind of interesting, if you ask me. So the prime numbers can only be divided by 1 and itself, or a prime number. A composite number then is anything that's not a prime number, but also 1 is also not a composite number. 1, the number 1, is neither prime nor composite. It's just weird. So your composite numbers would be like 4, because you can do 2 times 2 to get 4. 6, 8, 9, because you can do 3 times 3 to get 9. So prime versus composite numbers, this is good stuff to know. Well, very quickly, we can get to something called the fundamental theorem of arithmetic. And it states that every composite number, every non-prime number, can be expressed as a product of prime numbers in one and only one way. This is called the prime factorization of the number. We basically take a number and we break it down to its building blocks. We take a number and we break it down to its building blocks. So for example, if we had the number 48, you've probably seen something like this before, where you make a little prime factor tree. What are two numbers that multiply to 48? 2 and 24. And then what you do is you stop when you've hit a prime number. So 2 is a prime number, so it can't be broken down anymore to any further building blocks. What are two numbers that multiply to 24? 2 and 12. What are two numbers that multiply to 12? 6 and 2. And let's just adjust this. Give myself a little space. And then what are two numbers that multiply to 6? 2 and 3. So the prime factorization of 48, you can use, there's a 2, there's another 2, there's another 2, there's 4 total 2s in one 3. So I can write 48 as 2 times 2 times 2 times 2 times 3. And so this is said to be the prime factorization of 48. 2 times 2 times 2 times 3. What the fundamental theorem of arithmetic tells me is not only can I break a composite number like 48 down like this, but 48 can only possibly be expressed by this prime factorization, 4 2s and 1 3. And no other number will have a prime factorization that has 4 2s and 1 3 and nothing else. So perhaps that doesn't sound interesting, but it actually kind of is. Side note, we're going to be learning exponents in the course. We're going to be going over them. If you have 4 2s and they're all being multiplied to each other, you can write that as 2 to the 4th power. And then you can say it's times. You have 1 3, so you can say that's times 3, or you can even put 3 to the 1st. And it's the exact same thing. It's just a lot, we've shrunk it down a little bit. It's a lot easier to digest this way. So 48 is 2 to the 4th times 3. What would the prime factorization of 43 look like? It's prime, yeah, very good. So it's done. So the prime factorization of a prime number, you're done. There's nothing to do. You can scratch your head for a while, but you're not going to find two numbers other than 1 and 43, which multiply to 43. So the prime factorization of 43 is just 43. Or you can say, if you wanted to get cute with it, you can say 43 to the 1st, because there's just the one of them. So you can see they broke down 700 in a similar manner. 700, they said, is 7 times 100. 7 is prime, so anytime you get to a prime number, that's like a terminal node. It's a stopping point for that. But 100 can be broken down, 50 can be broken down, 25 could be broken down. I have a wonderful hint for you. I'm going to give you a hint, and it's going to be a painful hint because it is going to be something you will have to do on your own, but I promise you, if you do it, it is going to make your life easier. Memorize the 12 by 12 multiplication table. Maybe you already have it memorized. I remember when I was learning the multiplication table, we would listen to these corny little songs and they would try to do it in different styles. I remember the multiplication for fives, 5 times 1, 5 times 2. It was like a wannabe country song, but it's seared into my brain. I will never forget it. I will not sing it for you here because I'm too shy to do that. But yeah, I remember just sitting in school and listening to those songs. And so you're going to want to memorize the 12 by 12 multiplication table. You already got it? Very nice. If you don't, you can do it in 15, 20 minutes. Find a YouTube video that has some kind of snazzy little trick for teaching you or to remember the 12 by 12 multiplication table. But trust me, you're going to need to know that, especially for this course. I'm going to have to assume that you know the 12 by 12 multiplication table like the back of your hand. You can do 8 times 7. You don't even have to think about it. You could do 11 times 8. You can do 11 times 12 because it's just so fundamental to everything we're going to be doing, especially while we're talking about number theory. So that is my hint to you. So you can write 700 as 2 squared times 5 squared times 7 to the first, if you wanted, or just times 7. Now, the greatest common divisor is exactly what it sounds like. The greatest common divisor of two numbers is the largest natural number that divides cleanly into both numbers. You may have seen this one called the LCD. The LCD, perhaps. So let's look at the LCD. Let's look at an example of it. Let's say you had, how about, what's an interesting one? How about 36 and, how about 60? Here's some common divisors of 36 and 60. Let's see, would you guys say the number 2? Does 2 divide cleanly into both 36 and 60? Yeah, I'd say so. They're both even numbers. Is it the largest? No. What about 3? So these are still common divisors. They're just maybe not the largest. Does 3 divide into 36 and 60? Sure does. Is it the largest? 4 will work. 60 divided by 4 is 15. But is it the largest? No. The next one might just be 6. 6 will work. Does 12 divide into both of them? Yeah, I would say so. 12 divides into both 36 and 60. Can you think of a larger number than that? I'm thinking we can't. I'm thinking we're done here. 18 isn't going to work. 15 will divide into 60, but not 36. How do I know this? Well, kind of just based off my intuition. But intuition is not going to be good enough. So what I'm going to do, I'm going to show you a method for calculating the largest common, the largest common divisor or the greatest common divisor. And so I'm sorry, this is usually called the GCD. I literally wrote the wrong thing, sorry. The greatest common divisor. So for 36 and 60, 12 is going to be the greatest common divisor. It's the largest number that divides cleanly into both of them. And you certainly can't get any larger than that. But let's say you didn't trust me. Let's say you didn't trust me. So let's use a definitive method for finding the GCD. Take 36 and take 60. And now let's find the prime factorization of each to start with. So this definitive method is a bit of a pain because you've got a little bit of work to do, but it is going to work. It's guaranteed to work. So what are two numbers that multiply to 36? 18 and 2. We can do that, but that's going to make a nice long tree. Is there another? But that does work. You can certainly do that one. 4 and 9 will work. Let's do 4 and 9. Let's just mix it up. But 2 and 18 is perfectly good. It'll get you the same thing because there's only one way to do a prime factorization of 36. Now, what are two numbers that multiply to 4? 2 and 2. What are two numbers that multiply to 9? 3 and 3. So 36 is 2 2s and 2 3s. So it's 2 squared times 3 squared. We'll put a pin in that and we'll do 60. Use a different color. Let's find the prime factorization of 60. Can y'all think of two numbers that multiply to 60? 12 and 5, very good. 5 is prime, so we're done with the 5. How about 12? How can that break down? 2 and 6. The 2 is done, but it's still part of the prime factorization. And then 6 is what? 2 and 3, yeah, 3 and 2. Mm-hmm. Thus, 60 can be written as 2 squared, because there's 2 2s, 3 to the first, 5 to the first. Okay, we've found the prime factorizations. Here's what the GCD is going to be. It's going to be a little bit funky. The GCD takes each unique prime base. What are the prime bases? Well, this one, the bases are 2s and 3s. Here, the bases are 2s and 3s and 5s. So it takes each of the unique prime base and accepts the lowest number of representations, oh my gosh, I can't spell, of those bases. What in the world do I mean? Well, the GCD our prime bases, we got some 2s here. Here we have 2 2s, here we have 2 2s. We take the least representation, but they're tied. So the GCD is going to end up with 2 2s in it. Our next prime base is 3. This one has 2 3s. This one only has 1 3. So our GCD will just have a single 3. It'll go with the lesser representation. And then 5, well, this one doesn't have any 5s. You could say it has 0 5s. This one has 1 5. So that means the GCD is going to have no 5s in it. It's going to have the less represented of that specific base. And so we're done. The GCD is 2 squared times 3 to the first. Well, 2 squared is 4 times 3. And the GCD is indeed 12, which is what we found just by trying to think about it logically. So we have some fun. So you can find the GCD. Perhaps if you're quick with doing it in your head, you might just be right. But this is a method that is guaranteed to work. And you can apply it to any numbers. You can have 3 numbers and you can find their GCD through the same process. So if you want, you can write down these steps here. This is just a more eloquent way of explaining the steps we just went through to find the GCD. If you want to do that, that's cool with me. If you find 2 numbers whose GCD is 1, meaning you couldn't find anything really interesting that they had a common divisor, you call them relatively prime. Neither of them might be prime numbers, but they're relatively prime. They have no common divisor other than 1, and 1 is just not interesting. It's not every number is divisible by 1, so that's not interesting to say 1 is a common divisor. So relatively prime. So you could, if you wanted to, you could find the GCD of 216 and 234. Now you might scratch your head for a second because those are some pretty big numbers. 216 is certainly no small fry. 234 is certainly no small fry. So you might have to play around a little bit. You take 216, you can tell it's divisible by 2. And so you can just break down its prime factorization, and you'll see that 216 has 3 2s and 3 3s. 234 has 1 2, 2 3s, and then a 13. So this is the prime factorization of 216, 2 to the third times 3 to the third. This is the prime factorization of 234, 2 to the first times 3 to the second times 13 to the first. So you take the least number of representations. This has 3 2s. This only has 1 2. So the GCD is going to accept only 1 of those 2s. This has 3 3s. This only has 2 3s. So the GCD is going to accept just 2 3s only. This has no 13s. This has 1 13s. So the GCD is going to accept no 13s. It's going to accept the lesser of the representations of that prime base. And so the GCD will be 2 to the first times 3 squared, 2 times 9, which is 18. So the greatest common divisor of 216 and 234 is 18. So it's a pretty slick little system for finding the greatest common divisor. So we have the GCD, which is the greatest common divisor. It's the largest number that cleanly divides into your original set of numbers. whatever you're trying to find the GCD of. We also have something called the least common multiple, or LCD. I'm sorry, LCM. Wow. These silly little abbreviations, you kind of start to forget them. They kind of move around in your head. We find the least common multiple of, don't do that, a set of numbers by, come on, doesn't like me, listing out their multiples and finding the smallest one. Or there's a better method, which we'll go over here in a second. So for an example, let's find the LCM of 9 and 12. So what I'm going to do is I'm going to take 9. I'm going to list out some multiples of 9. In other words, I'm going to be counting by nines. 9, 18, 27, 36, 45, 54, 63. Again, here's where remembering your 12 by 12 multiplication table is mega helpful. Now it keeps going, but at some point, I have to limit myself. I'm going to also write out the multiples of 12 here, and hopefully I can find a common multiple between them. There we go, I just did it. But we'll keep going. I'll even add another one, or a couple more, to 9. So 9, 18, 27, 36, 45, 54, 63, 72, 81. Basically, you're counting by nines, if you will. 12 is 12, 24, 36, 48, 60, 72, 84. Notice a couple things. Let's use red. Notice that among those lists, 36 shows up twice. Thus, 36 is a common multiple. Common meaning it's found in both cases, and it's a multiple of both of those numbers. But look, 72 is also a common multiple of both of those numbers. And if you were to keep going, you'll see that so is 108, so is 144, so is 180. You'll find there's actually a lot of common multiples, but the most special one is not the largest because they can keep going and going forever. The numbers can just keep getting larger and larger. So the special one here is not the largest common multiple, it's the least common multiple. And that's what 36 is. So 36 and 72 and 108 are all common multiples of 9 and 12, but 36 is the least common multiple. That doesn't mean that that just means it's the smallest. So we can find the least common multiple of two numbers by just listing out their multiples. Well, what if you had the numbers, I don't know, 112 and 57? Look, you're not going to want to list out their multiples. They're going to be massive. Do you get to use a calculator for this 0332 portion of the course? No, we do not use calculators in this course. So any numbers you see on exams are going to have to be something that you can do without a calculator. You can use the methods you've learned in this class. When we get to the second half of the semester, the 1332 portion of the semester, we have to have calculators because there's literally calculations that we can't do without them, that I can't do without them. So anyways, this is one method for finding the LCM. And if your two numbers are relatively small, it's a good method. It's fine. But whenever you deal with larger numbers, it's not going to be a good method. So the better method, you're going to find the prime factorizations of your numbers, the numbers you're trying to find the LCM of. But unlike for the GCD, where you took the least represented of the prime bases, for the LCM, you take the most represented. You kind of flip it on its head. In fact, the process is almost identical or almost is very similar to the GCD, except you're going to flip it on its head. You're going to flip it on its head. So I'll give you about 10 seconds more to write that down. Well, I said 10 seconds. Do y'all have any questions about any of this so far? It is kind of coming at you quick. That's just how this course is going to go, unfortunately. There's no good way around that. So let's say you wanted to find the least common multiple of 144 and 300. So first you're going to need to find the prime factorization of each number. You can imagine the prime factorization tree. 144, if you know, 144 is 12 times 12. In fact, it's the largest number on the 12 by 12 multiplication table. And so once you know it's 12 by 12, you just break it into two 12s, then you break the 12s into two 2s and a 3, two 2s and a 3. You'll end up with 4 2s and 2 3s. 300, you can break that into 3 and 100. Then you can break down 100 as 10 times 10, if you want. So this would end up being the prime factorization of 300 here. Now, let's look at all the different possible bases between here. You've got some 2s floating around. You've got some 3s floating around. You don't have a 5 here, but you do have a 5 here. So the least common multiple, you're going to take the greater represented of that prime base. So here there's 4 2s, here there's only 2 2s. If I was doing the GCD, I would take the 2 2s. But if I'm doing the LCM, I'm going to take the 4 2s. And this is going to be what makes it into my LCM. Here I've got 2 3s, here I've only got 1 3. So here I got 2 3s, here I only got 1 3. Again, I'm going to take the greater represented of those. So I'm going to take 2 3s. Here I have no 5s. I have 0 5s, but here I have 2 5s. Even though 5 doesn't show up here at all, I'm going to take the greater represented, which is to say, I'm going to take the 2 5s. So my LCM is going to have 4 2s, 2 3s, and 2 5s. It's going to be a pretty beefy number. So the LCM is going to have 4 2s, 2 3s, and 2 5s. It's going to end up being 16 times 9 times 25. On your test, you may not get numbers quite as large as like 144 and 300, but technically you could do this using old school multiplication. You know, you do your 16 times your 9. Six times 9 is 54, carry the 5. 9 times 1 is 9, plus 5 is 4, so 16 times 9 is 144. Then we were doing 144 times 25. So technically you could do this one by hand. 5 times 4 is 20, carry the 2. 5 times 4 is 20, plus 2 is 22, carry another 2. 5 times 1 is 5, plus 2 is 7. Then you create another row, you give yourself a 0. Now you go with the 2s. 2 times 4 is 8, nothing to carry. 2 times 4 is 8 again. 2 times 1 is 2. Add 3,600. So 16 times 9 times 25 is 3,600. Which is just to say that's what the PowerPoint found. And so the least common multiple is 3,600. So the least common multiple is usually, it's ironic. The least common multiple is usually going to be a large number. The greatest common divisor is usually going to be a small number. But that's just the nature of it. That's because when you hear the word greatest, you're thinking of the greatest among small things. When you hear least common multiple, you're actually looking for the least among large things. So it's still going to be large, usually. So a cute little problem. A movie theater, what's that? What's a movie theater? Do people go to the movies anymore? Well, I went and watched all 8 Harry Potters in different movie theaters around DFW last year, but there was like nobody. It was just me and my girlfriend. We're just watching Harry, we're just nerding out. You know, we brought the books. We would have a book and like, oh, this is a Goblet of Fire, and we'd bring the goblet. How many of you have ever watched a Harry Potter? How many of you Harry Potter is actually not something you really got into as a kid? No, that's fair. I mean, it was huge when I was a kid. I'm like the exact same age as the guy who played Harry Potter. So, I mean, I was all Harry Potter as a kid. But anyways, that has nothing to do with this. So anyways, a movie theater runs its films continuously. One movie runs for 80 minutes and a second run one. So some kids movie is 80 minutes. Some superhero movie is 120 minutes. Both movies begin at 4 p.m. When will they begin at the same time again? So think about it. The 120-minute movie is going to be 120 minutes. So it's going to go from 4 till 6 p.m., then 6 till 8 p.m., then 8 till 10 p.m. But the 80-minute movie is a little bit weirder. It's a little different. It's going to start at 4 and go from 4 till, 5:20 p.m. And it's going to go from 5:20 until 6:40 p.m. And it's going to go from 6:40 until, so they're not quite in sync, but every once in a while, they're going to sync back up. So what you want to do is you want to find the least common multiple of 80 and 120, because you want to know when are they going to hit the same number again, the same number of minutes after 4 p.m. So you find the prime factorizations of 80 and 120. 80 has 4 2s, 120 only has 3 2s, but we take the greater represented. So the LCM is going to end up with 4 2s. Now 80 doesn't have any 3s, it has 0 3s. 120 has 1 3. So we're going to take the greater represented of the two, and we're going to end up with a single 3 end up in the LCM. Finally, this has 1 5. 120 also has 1 5. So 1.5 makes it into the LCM, and you end up with 240. So every 240 minutes, or in other words, every 4 hours, the movies line back up and they'll start at the same time again. So if they started at 4 p.m., they'll be synced back up at 8 p.m. That's 4 hours after 4 p.m. That's not so bad. All right, let me sync up our next. We get our next PowerPoint going. We're just having fun, aren't we? It's a Wednesday, right? It's Wednesday, right? Am I wrong? No, it is Wednesday. Okay, good. I do not claim to be good about memory. Well, I can remember the days of the week, but once you get into a zone, you just kind of you're dialed into that one little thing. You can forget little details. I don't know what my name is. I really don't. Is it Barry? Could be. I'm not ruling out Barry as a possibility for my name, and nobody else should either. But that's okay. All right. No, I know what my name is. It's James. No, it's not. Okay, back to the grindstone. So we just covered section 5.1. Now we're on to section 5.2. I'm gonna give you a hint, a bit of a hint. There is no rhyme or reason to the sections that we're gonna cover. We started with chapter 5, not chapter 1. We may not immediately go into chapter 6 after chapter 5. We might jump around. We might find all kinds of weird sections. The good thing is your homeworks do align with that. So I know what sections your homework covers, and I do know then what to cover in class. So the things you see in your homework do have a logical consistency to them. It's just that we may not go straight to chapter 6. We might do, we're going to do a random section from chapter 7, and then we're going to come back to chapter. It gets weird. The reason is because we like the textbook. The math department likes the textbook itself. We just like a different order for the material. We prefer it to be presented in a different way. So that's all it is. In fact, when we get to the 1332 portion of the course, we are going to do chapters 1, 2, 3, 8, 11, and 12. And that's just because that covers the material that is required for the 1332 class. Now I have to step out for one moment. Okay. So in the last section, we defined a set of numbers called the natural numbers. It's just the positive whole numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Here, we're going to define a much broader set. These are called the integers. The integers, you'll notice the integers are still, all the natural numbers are among them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, dot, 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 keeps going. But we also toss in 0. 0 is an integer. We'll call it 1 at least. And then we do all the negative numbers, the negative versions of the whole numbers. So -1, -2, -3, -4, -5, -6, -7, and so on. So that's kind of interesting. We're expanding them, but that means that the natural numbers are called a subset of the integers. They are a smaller piece of a larger puzzle in this case. So a few cool things, some things that may only interest me. The natural numbers have this weird little symbol. It's like an N, but there's a little gap here. So these are the natural numbers, which are just all the positive whole numbers. 1, 2, 3, 4, 5. So you can see why they use an N for natural. The integers are weird. They use a different symbol. It's like a Z. It's like a weird, funky Z. The reason they use that is because they use the German word for number, which is Zahlen, and it starts with a Z. That's literally why they do it. Why? I don't know why, but that is why, if you will. And like we said, so those are the integers, and those are just the negative versions of the natural numbers. They have 0 as well, but they also have the positive versions of the natural numbers. So basically, they can be positive, negative, or 0, but they are, can't use the word whole numbers, but it's like they're whole numbers, but it can be negative or 0 as well. So you're not going to get any parts of numbers, no halfway in betweens two other numbers, nothing like that, or not in the way you're thinking. So that's cool. We're learning some new types of numbers. You probably didn't know that, but in math, it's very important that we differentiate between different kinds of numbers. We're also going to expand that. We're going to learn later on in the course about something called rational numbers. We're going to learn about real numbers, and then rational numbers, and then irrational numbers, and then real numbers, and then I might briefly mention something called complex numbers. So you can look at this on a number line. So -1 is actually greater than -4 because it is to the right of -4 on the number line. That sounds weird because +1 is less than +4. That one's obvious. We can just tell. So 4 is greater than 1. But here, -1 is actually greater than -4 simply because it's to the right of it. So as I go from left to right, the numbers are getting larger. So the negative side of the number line doesn't start with negative infinity or anything right here. It starts with -1 and it works its way down that way. So if you took a single number line like this, you took a single number line. If you wanted to graph -3, you would just locate -3 on the number line, and you can just place a nice solid dot there, a point. Graphing the number 4 is also straightforward. Look for the number 4, and boom, you've got yourself a nice solid filled in dot there. And then finally, if you wanted to graph 0, same difference. 0 is just, it's the anchor, it's the middle point there. How many of you want to see something cool? Raise your hand if you'd like to see something cool. Raise your hand. Everyone go ahead and raise your hand. Everybody. We aren't afraid to look at a single number line. So maybe something like this. How many of you know what the Cartesian coordinate system is, or the XY coordinate plane? How many of you remember graphing things? We had to graph things, you had an x-axis and a y-axis. Both axes are just number lines. So you have the X number line or X axis, the Y axis. The problem is if they're both horizontal, I can't really place them on top of each other, and see anything special. If I try to place this on top, they're just overlapping each other, right? It's ugly. So what we do is we just rotate. It may not let me rotate. Nope. So what we're going to do, we're just going to have to rotate our y-axis so that they can fit on top of each other, and we can have two dimensions, two variables going on at the same time. So all the x and y axes they're just two separate number lines that are laid on top of each other. So I always thought that was a pretty neat little thing. All right, let's take attendance. Don't go anywhere just yet.